Hello, you all. Darrell Berry Jr. here, back for some more science, some physics in particular. And what I'll be doing today is going over some uh, undergraduate physics, uniform circular motion, and my qualification where I demonstrate my understanding of undergraduate physics. I get to work more on uniform accelerated motion. So I'll do some reading of that and prepare to ace that component of my undergraduate understanding. So that's where we're at. Impromptu stream. I'll see how long I go for. I'll still have the stream tonight. Is the plan. So I made a poll on the stream. So make sure to check the poll to let me know what you'd like me to cover tonight. I don't see any votes or anything. I'll just go ahead and decide. And we'll see what we'll do. And as far as I can tell, the audio seems like it's okay. Oh, I just realized I didn't change the image on the Witchmajinky. Hold up. Let me adjust that. So the book that let me change this image. The book that we're using is going to be University Physics 1. It's a free textbook. You can get it online, OpenStax. So a few of my classes that I work with have used this book. The EM class that I was a learning assistant for used it. And I'm pretty sure one of my other classes used it. So seems to me that their books are pretty good. I noticed today when I was setting up the image for it that there's some paperback versions you can buy online, but there's also like PDFs that you can download from their website. So it's pretty cool. So let's go ahead and get started. Whereas I can tell the audio is good. Let me check one more. Yep, everything looks good. So here we go. There we go. So what I have to do is get enough understanding to solve a pretty complicated problem, I will say, at least for me, till I get my better understanding of has a uniform accelerated motion, it has friction, angles. So we'll just work our way up. So 4.4. Circular. This is the chapter. Everything before this chapter I seem pretty clear on. And by the way, be sure to ask any questions, drop a line, let me know you're here. Any comments you have, I'll be sure to do the best I can. I hope you like the new setup for the reading and the sort of view I made. And in this section, you'll be able to solve for the centripetal acceleration of an object, moving on a circular path, use equations of circular motion to find the position, velocity, and the acceleration of a particle, executing circular motion. Notice it says particle, as I'm learning now in more detail in graduate school. When you have a system of particles, often you can model that system as if all the particles are in the center of mass. It behaves in that way. You can calculate a lot of things about it from that perspective. Explain the differences between centripetal acceleration and tangential acceleration, resulting from non-uniform circular motion. Evaluate centripetal and tangential acceleration in non-uniform circular motion and find the total acceleration vector. Uniform circular motion, when I'm here, uniform circular motion is a specific type of motion in which an object travels in a circle with constant speed. So UCF says uniform, that keeps it constant. Notice it says constant speed. That is not accidental. So I'll use, and for those who saw my show yesterday, familiar with this, just in case, let me note it again. If you see a bold V, I'm going with the vector notation. So that's a vector. And speed, by these double bars, I mean the magnitude. So if I put this, that stands for the magnitude of the velocity. And I'll just write that like a V without any arrow. So the idea is that this here, the velocity vector, it has a magnitude in a direction. So for instance, if I'm going to the right, I can define that as a positive velocity, which means that if I start going to the left, then that's a negative velocity. If I define it that way, if I define my axes that way. So even though the speed of each of these things can be the same, the absolute value of V is the same thing as the absolute value of negative V. The velocity will be different, diametrically opposed. So what they're saying is that the speed is constant, the velocity will be changing because it's turning, as we'll see momentarily. Any point on a propeller, for example, any point on a propeller spinning at a constant rate is executing uniform circular motion. Other examples are the second, minute, and hour hands of a watch. It is remarkable that points on these rotating objects are actually accelerating, although the rotation rate is constant. To see this, we must analyze the motion of vectors, as I was hinting at earlier. Centripetal acceleration. One-dimensional kinematics. Objects with a constant speed have zero acceleration. However, in 2- and 3-dimensional kinematics, even if the speed is constant, a particle can have an acceleration if it moves along a curved trajectory such as a circle. In this case, the velocity vector is changing, or dv over dt equals not zero. So circular motion, constant speed, not velocity, because the velocity is changing. This is shown in figure 14 as the particle moves counterclockwise in time changing t on the circular path. Its position vector moves from r to rt to rt plus changing t. The velocity vector has constant magnitude and is tangent to the path as it changes from b to v t plus changing t, changing its direction only. If the velocity vector t is perpendicular to the position vector, the triangles formed by the position vectors and change in r and the velocity vectors change in v are similar. Furthermore, since the magnitude of r equals the magnitude of rt change in t, in v, the magnitude is v equals v change in vt change in t, the triangles are isosceles. From these facts, we can make the assertion that change in v over v equals change in r over r, or v equals v over r change in r. So we need to look at this. It might help to have the image that they're talking about in place. So what I'll do is redraw this, and then we'll look at it more closely. So we have a circle, and I'll see if I can make this easily the center of the circle. So the way I have this set up, seems like this point is the center. I have 1, 2, 3, 4, 5. Maybe I should mark these. 1, 2, 3, 4, 5 that way. 1, 2, 3, 4, 5. All right, so we see that that's the center. And so this is C. We have a vector that they put here. We have a vector that they put here. We have the tangential velocity vector. So if this is going on a perfect tangent going through those, then this arrow would be going on a perfect tangent like that as well. Except it'll just be positioned at the end of the circle here. And started at the tip. And I'll test something. I should be able to just rotate this 90 degrees and it should be perfect. There we go. And the same thing, I should be able to rotate this 90 degrees and it'd be perfect. There we go. And a vector here between these two. I guess I could erase these markers I put here. Create a triangle. We have the triangle RT inside the circle already. So I'll pull these out. All right, so we have all our circles. We have, this is the change in angle between the position of the particle as it goes around. We have, this is RT plus change in T. This is RT. This is change in R. This is VT. This is VT plus change in T. Change in V. VT V T plus change in T. This is change in theta. All right, so let's see if I have everything there. We have the center, change in theta, RT plus change in T, change in R. We have VT plus change in T. We have VT. We have VT plus change in T, VT, change in theta, change in V. It says a particle is moving in a circle at constant speed, position and vector vectors at times T and T change in T. Velocity vectors forming a triangle. The two triangles in the figures are similar. The vectors change in V point toward the center of the circle and the limit as T changes to the change in T equals 0. Interesting. All right, let's go back to the text they were saying. As a particle moves counterclockwise in time change in T, so the particle was here at time T, and after a change in time, which they're calling change in T, it ends up there. So this is T, this is T plus change in T seconds. On a circular path, the position vector moves from RT, where the particle is, to RT plus change in T. The velocity vector has constant magnitude and is tangent to the path as it changes from VT, which is this vector here, to VT change in T. So we can see that the speed of this vector is constant. The length is the same. We know that because I copied the same vector, but the direction has changed. So basically the particle was going some amount to the right, and now is going 0 to the right. So just from looking at the uh, horizontal direction, we can see that it went from going that way to stopping and going the opposite direction in the horizontal direction. So the velocity there changed, changing its direction only. Since the velocity vector is perpendicular to the position vector, as we see this here, the velocity vector is coming out. The position vector is coming out. The velocity vector is perpendicular. The triangles formed by the position vectors and the velocity vectors are similar. So it's interesting that the change in theta here between these two is the same as the change in theta here between these two. And of course, they're all at right angles to each other. So if they're right angle to each other, whatever degree one changes by, the other one has to change by. So that makes sense. Furthermore, since RT equals RT change in T, in other words, the length of this vector is the same as the length of this vector because it's uniform circular motion, so it makes a perfect circle. And that makes sense as well. It's going at uniform circular motion, so the speeds of these vectors is the same. The speed is the same going all the way around. The two triangles are isosceles. I don't even remember what isosceles is. That mean that two of the sides are, let's see. Isosceles triangle is a triangle with two sides of equal length. Okay. And perhaps I could have clicked the dictionary there. So any triangle with two sides of equal length is isosceles, from the Greek, equal leg. Isosceles, they have two equal legs, two sides of equal length. From these facts, we can make the assertion that change in V divided by V equals change in R divided by R. That makes sense? That the angles, they're in right angle to each other. So however much the R angle changes, the V angle will change by the same exact amount. So that means that the relative distance between the two will be the same. So the ratio should be the same. So we have the speed and change in V is the uh, difference in velocity. Change in V over V equals change in R over R. So change in V equals V change in R over R. Equals V over R. Change in R to write it a different way. Or change in R over R. You can find the magnitude of acceleration from oh, still have to work on my limits. Maybe I need to do a video on limits so I can brush up on my limits. You can find the magnitude of acceleration from A equals the limit as change of t approaches 0 of change in V over change in t. Which is V over R, the limit as change in t approaches 0 of change in R over change in t. Should I mean I have no idea what they're doing there? Okay, looks like they replaced change in V with V change in R over R. So now we have the limit as change in t goes to 0 of change in R over t. Change in R over change in t is velocity, instantaneous velocity. So I see it's an interesting way to do that. So A, acceleration, equals the limit as the change in t approaches 0. So we get the instantaneous acceleration of change in V over change in R. So acceleration is the change in velocity. Okay. And from here, we know that change in V equals the change in R over R. We still have 1 over change in R. So that equals Write something incorrectly. Yeah, this would be changing t. And since v and r are not changing, we can pull those out of the limit. So the vr that's changing t approaches 0 instantaneous of changing r over changing t. Changing r over changing t is velocity. So that's v over r times v, or speed in this case. So we have v squared over r. We have the angular acceleration as v squared over r from the taking the limit. The direction of the acceleration can also be found by noting that as change in t and therefore change in theta approach 0, the vector change in v approaches a direction perpendicular to v, as we see here. Since v is tangent to the circle, the acceleration dv over dt points toward the center of the circle. Summarizing, a particle moving in a circle at a constant speed has an acceleration with magnitude ac equals v squared over r. And this is equation 4.27. All right, so this is the stuff I need to learn. The direction of acceleration vectors toward the center of the circle. This is a radial acceleration, and it's called a centripetal acceleration. As an aside, you have something going around in a circle. Let's say a ball being swung around a string. If it's going inside, it's centripetal, and the force is going outward is centrifugal. Which is why we give it the subscript C. The word centripetal comes from the Latin word centrum, meaning center, and petere, meaning to seek, and thus takes the meaning center seeking. So acceleration is along the radius. Trying to get a better trying to get a better understanding of the logic behind their center of crap. Only this works. Right. Let me manually go back. By noting that a change in the approach changes the eta approach to 0, like perpendicular to P. As the change in T gets smaller and smaller, this angle here gets smaller and smaller, and the change in V is perpendicular to V. Since V is tangent, to the circle, the acceleration points to the center. It makes sense. Hmm. Centripetal acceleration vector points towards the center of the circular path of motion, as in an acceleration in the radial direction. The velocity vector is also shown and is tangent to the circle. Let's investigate some examples to illustrate the relative magnitudes of the velocity, radius, and centripetal acceleration. All right. So we have creating an acceleration of 1g. A jet is flying at 134.1, with that 0.1 there, meters per second along a straight line, and makes a turn along a circular path level with the ground. What does the radius of the circle have to be to produce a centripetal acceleration of 1g on the pilot and jet towards the center of the circular trajectory? The centripetal acceleration equal to gravity. So we have AC equals v squared over r equals 9.8 meters per second squared. So now we have 134.1 meters per second squared over r equals 9.8 meters per second squared. So the radius equals 134. So just write it like normal. Meters over second squared over 9.8 meters per second squared. And that equals 1.835 kilometers. Write that answer a little bit better. To create a greater acceleration in g on the pilot, the jet would either have to decrease the radius of a circle trajectory or increase its speed on its existing trajectory. Check your understanding. A flywheel has a radius of 20 centimeters. What is the speed of a point on the edge of the flywheel if it experiences a centripetal acceleration of 900 centimeters per second squared? So basically, we're just inserting it into the same formula. Centripetal acceleration can have a wide range of values depending on the speed and radius of curvature of the circular path. Typical centripetal accelerations are given in the following table. Okay. Earth around the sun. Why don't we calculate that? That seems fun. All right. So we have AC, Earth around sun. So we know that the radius is roughly 93 million miles from Earth to the sun. And let me convert that. I'll use an online calculator. So that's equals 1.47 times 10 to the 11 meters. We have, I calculated the speed of the Earth around the sun in one of my astronomy classes, but it won't take too long to calculate again. So C equals 2 pi r. So that's going to be, let me get my calculator. We shall recalculate what this is. We have 2 pi, then 1.497 times 10 to the 11. So that's 9.4 times 10 to the 11 meters. So we know it takes 365 days. So 1 year to go around that circumference. And that's 1 year is 365 days. And 1 day is 24 hours. And 1 hour is 60 squared seconds. So let's see what this is. That's 3.1536 times 10 to the 7 seconds. So we're going 9.4 times 10 to the 11 meters divided by 3.1536 times e to the 7 seconds. So that equals 2.98 times 10 to the 4 meters per second. All right. So going about 30,000 miles per hour around the sun, which um, seems similar to what I remember before. 30,000 miles going for the 10. So in other words, this is the green arrow velocity of the Earth. About 30,000 excuse me, 30,000 meters per second. Let me see what that is in miles. Okay, about 18 miles per second. 19 miles per second. It is pretty fast. So we have AC equals V squared over R. So that equals 2.98 times 10 to the 4 meters per second divided by 1.47 times 10 to the 11 meters. The squared equals, let me check, everything seems to be good. So we have this squared divided by 497 E11. So I got 5.94 times 10 to the negative 3 meters per second squared. which is pretty much what the book got. So the book got 5.94. I got 5.93. I did some rounding on the uh, radius of our orbit. Sure, that's not precisely right. It must be a little bit large, maybe small. I'm not sure which way to go. I have to think about it. Oh, yes, that's awesome. Good calculation. So this is the centripetal acceleration of Earth around the sun. A simple calculation. Moon around Earth, satellite in geosynchronous orbit, outer edge of a CD-wind plane. Wow, that's less than gravity, but jet on a barrel roll. Wow, roller coaster. 5Gs. Electron orbiting a proton in a simple Bohr model of the atom. That's crazy. Acceleration orbiting a proton in a simple Bohr model of the atom. Many G's. So that shows the strength of the um, strong force. Is it the strong force? I don't know. I don't know which force it is that keeps the atoms together. Seems like it's a strong or the weak force. One of them, they're strong. All right. Equating the motion for uniform circular motion. I actually used this problem for one of my classes, by the way, calculating the centripetal acceleration of the Earth around the Sun, and maybe even some of the other planets. Pretty fun problem. A few steps of calculations. The radius is known, measured, calculate the circumference, which is the route, convert a year, uh, get the speed of the Earth around the Sun, then just plug into the formula for centripetal acceleration, and we have the centripetal acceleration. It's pretty good. A particle executing circular motion can be described by its position vector. According to this, figure 4.2 shows a particle executing circular motion in a counterclockwise direction. This particle moves on the circle. Its position vector sweeps out the angle theta with the x-axis. Vector r, t making an angle theta with the x-axis is shown with its components along the x and y axes. The magnitude of the position vector is a equals the magnitude of r and is also the radius of the circle, so that in terms of its components, if you're not clear on that, let me know. There's some pretty basic, trigonometry, I think that is. Theta, RT cosine theta, RT sine theta. Okay. Theta is WT, radians per second times seconds. Maybe I do need to write this out. So we have a vector here, and it's two components. So it's making an angle with the x-axis. So cosine theta equals uh, adjacent over hypotenuse. So that's x over r. So x equals r cosine theta. Y equals r sine theta. And we know velocity is the distance you travel over time. So distance is vt. For here, we're going to angles. So that's the angular velocity times second. So that's radians per second times second as far as the units that are going on here. I think radians is actually a unit, but we'll still put it in the box. So I'll also plug that in. Let's see how the book gets what they have. X equals omega c cosine theta. Y equals omega t sine theta. And R equals omega t cosine theta I plus omega t sine theta j. Oh, hold up. I guess technically it'll work, but distance around. So as time goes on, over so many radians. So this is the distance that's covered. The d equals vt is actually what circumference or what arc, remember what the arc equals omega c. And technically it's still not the length, it's just the angles. Let me look at this. Here, omega is a constant called angular frequency of the particle. Angular frequency has units of radians per second and is simply the number of radians of angle measure through which the particle passes per second. Right, so we do have that, radians per second. The angle theta is the position vector. Angle theta that the position vector has at any particular time is omega t. Which makes sense. It's going through so many radians per second. You multiply the seconds, then you have how many radians you went through. And how many radians is theta? says theta equals omega t. And okay. But it's that's right. But it's taking the magnitude of this, the magnitude of A, the vector, uh, wouldn't work out. A better understanding of angular frequency. T is the period of motion or the time to complete one revolution 2 pi, then omega equals 2 pi over t. Let's think about that one. Okay, that makes sense. Because 2 pi omega is radians per second, and to complete one revolution is 2 pi for one revolution over the time it takes to complete one revolution, which is the angular frequency, and t. Just theta over t. How much theta over how much time? 2 pi radians over the amount of time it takes to cover 2 pi radians. Angle theta is the angular frequency of w in radians per second multiplied by t. Velocity and acceleration can be attained from the position function by differentiation. All right. So b r over dt equals v t equals r time t I, and that's minus omega plus r cosine omega t j. We have omega, so that looks to be right. I'm just going to call my magnitude of r using the convention that I established earlier. And let me angle this a little. And we have, it can be shown from figure 420 that the velocity vector is tangential to the circle. Crap. Apparently it's very easy to do that when you're clicking. We see it was going back for a while, but not enough. From this equation, we can see that the acceleration vector has a magnitude. It can be shown from figure 420 that the velocity vector is tangential to the circle at the location of the particle with magnitude AW. Okay, that makes sense. So omega is radians per second. Does that make sense? Oh, that's right. Radians is not a unit. I mean, it is a unit, but it's it's, it's almost like a virtual unit. Thinking about the verbiage from our graduate class. So you have a omega, so that equals meters radians per second. So that equals meters per second. It's because we know with the circumference, 2 pi r is the circumference. So the radius is going to determine how fast in linear space that particle moves. Because the radius is faster, and the radius is going to be determined by the magnitude of r, which is the radius. Okay, makes sense. Similarly, the acceleration vector, the v over dt equals a t equals negative omega squared r cosine omega t I minus omega squared r sine omega t j. This is 4.29, 4.30. In this equation, we see that the acceleration vector has a magnitude a omega squared, and it's directed opposite the position vector. Let's look at figure 420. I'm getting the I mean understand from earlier why the acceleration will be towards the center, because the changes in velocity, the angle between them as it approaches zero, the angle gets smaller and smaller, so the change in v between them is going to be perpendicular. And we know that the velocity is already perpendicular to the radius. So you have perpendicular to the radius and perpendicular to that. So it's going towards the center. But it seems like they're utilizing, showing that the velocity vector is tangential to the circle. What they say is to show it, and that's not necessarily using this plus minus here. In this equation, we see that the acceleration vector has a magnitude of a omega squared. Right? Makes sense. And it's directed opposite the position vector towards the origin. because A equals negative omega squared RT. So they're basically doing is negative omega squared cosine omega t I plus r sine omega t j. And it is in fact the position vector multiplied by negative omega squared. And thus we know it's going directly opposite the position vector, the radius vector, except it's scaled by negative omega squared. It would be scaled by omega squared. The negative is there. Hmm. All right, you're going to circular motion of a proton here. We do this and then we'll call it a day here. Circular motion of a proton. The proton has a speed of 5 times 10 to the 6 meters per second. So what is that? 5 million meters per second? Believe so. And is moving in a circle in the XY plane of radius 0.175 meters. What is the position in the XY plane at time t equals 2 times 10 to the negative 7 seconds, or 200 nanoseconds? A nano was negative 9. Oh, it says 200 nanoseconds. So I made it 200 to bring it down to nano. Okay. At t equals 0, the position of the proton is 1.75 mi and the circle is counterclockwise. Sketch the trajectory. When we get the proton has a period of angular velocity of p equals 2 pi over omega. Omega is theta t. Maybe I do need to look at this. So the period is 2 pi over omega. But how I'm saying omega is v over r. It's radians per second. Right here did they say omega's velocity over radians? Angular frequency. V is d over t. What is velocity over radius? Radians. So they're saying that example 4.11 period equals equals 2 pi over t. So t equals 2 pi over omega, which they also equal to 2 pi r over b. So that means 1 over omega is r over v. So omega is radius over tangential velocity. Over a second divided by meters. The radius, the slower it's going, the slower the angle changes, because omega is also theta per second. Does that make sense? Or theta over t. The velocity, tangential velocity divided by radius, ends up giving you radians per second. Piece c is v squared over r. Divided by v, 1 over a second. Okay. I just need to keep this relation in mind. I wonder if it's on the formula sheet. I don't remember. I'll check really fast. On the sheet, so for our exams, we have a mechanics formula sheet. Has a lot of good stuff on it. I see the angular acceleration one, which I saw on the exam. So they have AC equals v squared over r, which is r omega squared. So we can say v squared equals r squared omega squared. Taking this and take a square root of both sides, we should have v equals r omega, and thus omega does equal v over r. Isn't that something? Right. That means that with these equations, I should probably remember that AC equals v squared over r equals r omega squared. I wonder how I can just remember that detail. And it is on the formula sheet. And albeit in a different form. Omega is 2 pi over t. Position of the particle. So add in the position. This is definitely interesting. So I have to remember when I do the position thing to take the vectors of position with respect to angular acceleration. Details to remember. All right. So I think I'll go ahead and call it here. Hopefully you all enjoyed and learned. Make some comments, subscribe if you haven't. Help me get to 1,000 subscribers. And I'll still be back tonight for the normal show. I'll see what I end up doing. Maybe I'll continue some of this or do something else. Thank you all for watching. Have a good day.